So this is Chemistry 108, Chemical Principles 1. We're continuing our discussion of Chapter 1. This is February 3rd, 2015. Last time we left off right around here, different properties of matter. So last time we looked at, we thought about what is chemistry, right? Chemistry is the study of matter. And you guys came up with different definitions of what matter is. Some of them were more formal, some of them were less formal. What is matter? Matter is stuff. Matter is, and that's true, right? Matter is the stuff all around us. And we looked at we looked at chemistry as a central science. Chemistry has a significant role in many other fields of science, in biology, astronomy, physics, engineering, more applied things like forensic science, criminal justice, military science. Chemistry is quite central because chemistry addresses matter, and matter is basically the physical material of the universe. Formally speaking, matter is anything that has mass and takes up space. And we saw that one thing that chemists do is classify matter, right? And so we looked at different states, solid, liquid, gas. We looked at pure substances versus mixtures. And for mixtures, we looked at homogeneous mixtures, heterogeneous mixtures. And we started looking at properties, right? How do you describe matter through its properties? And we came up with some. Here's the list that I had on my slide. You guys came up with some other ones as well. Mass, volume, and so on. Color, odor, density, and so on. And we started looking at dividing up these types of matter, or these types of properties. We have physical properties, and we have chemical properties. And if you recall, physical properties are those that can be measured without changing the identity or composition. And so how do you find the mass of an object? You put it on a balance. You put it on a scale. How do you find the volume of an object? You can measure it. If it's water, if it's a liquid, you can just pour it into a measuring cup or a graduated cylinder. What if it's a solid? How do you measure the volume of a solid? Some of you might have done this in lab already. Sorry? I saw someone's mouth moving.
Place it into a water beaker.
Yep.
And then you would subtract the difference.
Right. So you could place it into a cylinder or some other graduated piece of equipment. Already has water in it. You put your solid object in. The water goes up. How much it goes up is equivalent to the volume of the object you put in. Chemical properties, they have to do with how a substance reacts with other substances, right? How do you tell if something is flammable? You have to try to set it on fire, right? How do you tell if something is acid? There's different ways. Generally speaking, or broadly speaking, you want to react it with another substance called a base. And when we get to chapter 4 or so, we'll look quite a bit more at acids and bases. There's other ways to, this we covered last time, right? There's other ways to think about properties of matter. Mass and volume are what we call extensive properties. And extensive properties are those properties of matter that can change based on the quantity of a substance, how much there is. Right? So I have a certain amount of water in my water bottle. It has a certain mass and a certain volume. I take a drink. Now the mass, it's still water, right? But the mass has gone down and the volume has gone down. Right? So those properties depend on how much stuff there is. The rest of these we can basically call intensive properties. So an extensive property is one that can change based on the amount of a substance. What's an intensive property? Right, it stays the same. It doesn't change regardless of how much stuff there is. One of the simplest ways to look at this is melting and boiling point. Right? We know water boils at 100 degrees Celsius or 212 Fahrenheit, and water freezes at 0 degrees Celsius or 32 degrees Fahrenheit. It doesn't matter if you have a drop of water, a cup of water, or an ocean, right? As long as it's just pure water, the melting point is the melting point, and the boiling point is the boiling point. Density. We'll look at density. Density is also a very common intensive property. Density, as we'll see, has a component that has to do with mass, a component that has to do with volume. Mass and volume are both extensive, but when you put them together to get density, becomes intensive. So the density, again, if water is of a drop of water, is the same as the density of a gallon of water. And so on for all of these different properties. So intensive properties do not depend on the amount of substance that there is. You have a little bit, you have a lot. Melting point's the same, density is the same, right? You have a little bit of alcohol, a lot of alcohol, they're all flammable. You have a little bit of lemon juice, you have a lot of lemon juice, they're all acidic. There any questions so far? Okay. So, properties. Many properties of matter are quantitative and can be measured. So quantitative has to do with, comes from this word quantity. Quantity means how much, right? Or describes how much of something there is. So which of these are quantitative? Which of these can be associated with a number? Mass certainly can be associated with number. Volume, density, melting and boiling points. Acidity can, but it's not immediately obvious how. We will learn how. Color actually can be associated with a number in some cases, depending on how you measure it, or depending on your perspective. Well, green is green, right? Green is not necessarily a number, but we will learn in chapter 8 or so chapter 8 or so, how colors can be associated with particular values. And so some of these are very clearly quantitative. Some of them are quantitative in ways that are not quite so obvious. Some are quantitative, or maybe, for example, odor. Odor, again, it's you can quantify how much of an odorous substance there is, but the quality of odor, whether it smells good or whether it smells bad, that's something that's qualitative, right? There's no number attached to it.
What about the strength of odor?
The strength of an odor is something that you can quantify, right? But the actual type of fragrance is something that you can't, right? How much, what kind of, you can't really associate a number with like roses, right? So many properties of matter are quantitative and can be measured. So let's think about measuring properties of matter. And I like to think about it in terms of questions. Right? When we make a measurement, we're starting to do some, we could potentially anyway be starting to do some science, starting to do some experiments. So if I have a question, how hot is it outside? Or in this case, how cold is it outside? The answer, what I'm really asking in terms of properties of matter, is what is the temperature of the air outside? Right? Temperature is a property of matter. And the answer might be something like 25 degrees Fahrenheit. Right? Hopefully it doesn't get that much colder than that. The answer has two components. The first component is a number, 25. The second component is a unit. In this case, the unit is degrees Fahrenheit. If I were just to say 25, that's not a complete answer. What's the temperature of the air at 25? 25 what? 25 feet? No. 25 degrees Celsius? No. 25 degrees Fahrenheit. How far is it to my office? What property of matter am I really measuring if I ask, or am I really asking about if I say how far is it to my office? Distance or length, right? What is the distance or the length of the hallway between this classroom and 3F01? And I didn't measure it, I'm making this up, something like 17 meters, probably. I used to be in Forum 06, which is a lot closer than Forum 05. So again, you have a number and a unit. Right, if I just said 17, well, it's not clear. 17 inches is like from here to here to there. That's clearly not going to take you to my office. 17 miles is not going to do it either, right? 17 miles is going to be from here to like New Jersey or something. And so, at the risk of belaboring the point, when we measure a quantitative property of matter, we have a number and a unit. Always have a number and a unit, except when I tell you we don't. And we'll see a few instances where we don't have a unit. But when we make measurements, what we have is a unit. It tells us what exactly is being measured. Right? Is it inches? Is it feet? Is it miles? Is it centimeters? Is it pounds, ounces, kilograms? And a number. Right? So how much of what exactly it is that's being measured, and how much or how many of them there are. So what does that mean? That means, practically speaking, if you have an exam and you do the calculation right, and you write down the number without the appropriate unit, the answer is not complete. Not totally wrong, of course, but it's not complete. Also, practically speaking, we talked about this last time. Right? There are many of you who would like to be doctors, nurses, physician assistants. Not understanding units is one big reason why patients die. Right? I was supposed to give them micrograms, and I gave them milligrams of a particular drug, and they got 1,000 times too much. Okay, so what are some quantitative properties of matter? Well, we talked about them. Some of them: length, the measure of distance. Length, different measures of length could be the meter, inches, feet, miles. These are just some examples. Mass is a measure of the amount of material in an object. Right? We could measure it with a balance. Some of you used a triple beam balance, I think, in lab. It could be grams, kilograms. Pounds. Pounds is not really mass, right? Pounds is a unit called weight. And the difference between between weights and masses is that a mass measures the amount of material in an object. A pound depends on, and that doesn't depend on anything. A gram is a gram anywhere. But a pound is an amount of force. Right? A weight is an amount of force that's exerted on the material in an object. On the level of everyday life, they're roughly equivalent. Right? So if you step on a scale, it might tell you your weight in pounds. It might tell you kilograms, right? Especially if you're not American and your scale is not American, it might tell you kilograms. Why is that? Because where does the force come from? The force comes from gravity, right? And so we all live on the planet Earth, although I've met a few students where I was, kind of wondered. But I assume we all live on the planet Earth. So we all experience the same gravity, give or take very, very small amounts, depending on kind of where you are on the Earth. But you live on the Earth, pounds and kilograms, weight and mass can roughly be interconverted. Now, if you go to the moon, different story. And maybe one day that will become a commonplace exercise, but not yet. Time is the measure of the duration of an event, right? And so what are some units for time? Seconds, hours, minutes, years, right? I spent 2 or 3 minutes talking about mass. It may have seemed to you like 2 or 3 years. What are some other quantitative properties of matter that, well, we talked about some, right? We talked about volume, density. Any others you can think of? Acidity. So, right. So acidity, we could talk about something called the pH scale, how acid something is. Sorry? Decaying properties. Yes, so that's a very, if you're thinking about, say, like radioactive material, different radioactive materials have different, what are called half-lives. It's how long or how fast it is that they decay. And those are properties of a particular species of uranium or radon or whatever.
What about temperature, like joules?
Okay, so those are two things. Temperature certainly is quantitative. Right? Joules is actually a measure of energy. Right? Energy and temperature are not quite the same, although there's a relationship there, and it's also quantitative. So temperature, the measure of the hotness or coldness of an object. It's different units that we use for temperature. Kelvin, degrees Celsius, degrees Fahrenheit. If you grew up in the United States, degrees Fahrenheit is what you're most familiar with. It's what they report to you on weather.com or on the radio or whatever, wherever you get your weather report. They report it in degrees Fahrenheit. Most of the rest of the world uses degrees Celsius. In the lab, we generally use either degrees Celsius or a scale called Kelvin. So Kelvin is typically not used outside of the scientific enterprise, scientific world. And Kelvin and degrees Celsius, as we'll see shortly, are related to one another. Let's go back here. Because one of your colleagues mentioned heat, or joules, right? And let's think about temperature. Is temperature an intensive or extensive property? What do you think? So, I see you flipping back. What does intensive mean? It doesn't change regardless of the amount of stuff you have, whereas extensive depends on the amount of stuff you have. So temperature, intensive or extensive? Extensive, why?
What about like air pressure and stuff like that? What's happening in the environment can affect the humidity?
Okay, so that's not exactly temperature. So let's think about temperature and heat. Right? We haven't really thought about heat very much, or energy. Let's say I start a fire, right? And I burn a little tiny scrap of paper. And it reaches, I don't know, in this very small space, let's say, probably not this small, but if I burn a piece of paper and it reaches, I don't know, 1,000 degrees Fahrenheit, that reaches a certain temperature. And then, I'm not recommending any of you do this, and then you set fire to the room, and the whole room goes up, and it's also 1,000 degrees Celsius, or 1,000 degrees Fahrenheit. They're both the same temperature. Is it intensive or extensive? Why is that? Right, it doesn't depend on the amount of, in this case, fuel or fire that there is. So therefore, it's actually intensive. Setting the room on fire gives you more heat. That's extensive. Right, setting the paper on fire gives you a little bit of heat. You know, if you tried to set the paper on fire and you tried to boil water, you wouldn't get very far, assuming nothing else caught on fire, because the fuel it would get burned up and it would go out. But if you set the room on fire, you could certainly boil lots and lots of water. Right, there's much more heat there. Okay, so properties of matter. So this is what we've seen already. Right, numbers and units. Another property of matter, volume. Volume is a measure of the amount of space contained within an object. So again, these are things that many of you may already have a sense of probably what a volume is, what a mass is, what a temperature is. But now we're trying to formalize them, put a precise definition around them, and then so we can sort of better apply them to chemistry. So volume is a measure of the amount of space contained within an object. And now if you took geometry or pre-calculus, then you learned a lot about the volumes of different objects, right? The volume of a sphere, the volume of a cube, the volume of a rectangular prism, and so on. We're not going to do all of that. We'll just take a very quick look at volume. So this is a cube, right? So this is supposed to represent a cube. And the volume of a cube, or a volume of a solid object that is rectangular on all sides, is going to be length times width times height. Right? And so that's going to be, well, the first formula that you learned in chemistry. And again, many of you may be familiar with this, the volume of a rectangular prism, length times width times height. I'm doing this to show you something specific. So let's say, for example, that this particular cube is 1 meter by 1 meter by 1 meter. So what's the volume? So the volume, okay, on or off? Okay, so the volume, length times width times height. What's the length? Times width times height. Now, this may be one of the simplest calculations you'll ever do in chemistry. It's 1 times 1 times 1. 1. So what's the volume of the cube? Okay, so some of you are getting ahead of me. Some of you said 1 meter, some of you said 1 cubed. This is not exactly how you want to write it out. Why is that? Because measurements like meters need to have a number and a unit. So I failed, right? So 1 meter times 1 meter times 1 meter. So it's actually not quite as straightforward, yes? Exactly. She knows what she's talking about. She just doesn't know she knows what she's talking about, which is okay. 1 times 1 times 1 is indeed 1. But you also have to do, because I told you we have numbers and units, meters times meters times meters. Now the way that we write that is simply meters cubed. Right? The superscript, this is called an exponent. And if you don't recall your exponents very well, then Alex is the place to go. But what does this mean? This means essentially meters times meters times meters. It's whatever is the exponent is next to times itself that number of times. So it's meters times meters times meters. So the volume is 1 meter cubed. It's not 1 meter, it's not 1 cubed, it's 1 meter cubed. Same figure, right? So, yep. And you have a number and a unit. Questions so far? This type of manipulation of units mathematically is going to be an idea that really drives not necessarily your understanding of chemistry, but your ability to solve problems, right? So if you've taken a little bit of chemistry or physics or you've before or you remember you remember something from high school, some of what I'm telling you may be repetitive, maybe you didn't do it exactly this way when you learned it the first time. There's a reason why we're presenting it the way we're presenting it, because it builds, right? And by the time we get to chapter 3 and 4, then you'll realize, oh, the professor probably was making some sense. So students ask me, do I have to do it the way you showed me? Well, no, but you better get it right if you don't. Okay, so 1 meter cubed. You'll see what I'm talking about soon. Okay, so now let's say it's the same image, of course, but now let's say instead of 1 meter, each side we're going to say is 10 centimeters. What's the volume of the cube now? It's going to be 10 centimeters times 10 centimeters times 10 centimeters. What's 10 times 10 times 10? 1,000. What's centimeters times centimeters times centimeters? Centimeters cubed. Very good. 1,000 centimeters cubed. You have a number and a unit. 1,000 centimeters cubed is also known as a liter. Right? This liter is the same liter that refers to your soda bottle. Right? If you have a 2-liter bottle of soda. In a 2-liter bottle of soda, there's 2 of them, so it's 2,000 centimeters cubed. If you have a smaller one and it's only 1 liter, 1.5 liters, you have 1,000 or 1,500. One centimeter cubed is equivalent to what's called a milliliter. These equalities, I'm giving them to you now because they're going to come up again as we progress through chemistry. Sometimes, particularly in the medical world, a centimeter cubed is written as cc, right? Cubic centimeter, centimeter cubed. That's kind of scientifically speaking, that's considered not really precise, not standard practice. But again, within the medical world, a lot of times they'll talk about cc's rather than centimeters cubed. It's a shorthand that's commonly used. We're not going to use it in this class. This is probably the last time you'll see cc, that you will see cc. That wasn't Spanish. But for those of you who go on to work in hospitals, so you know what they're talking about. So the cube above has a volume of, we can write it in several different ways. Right? We can write the volume as 1,000 centimeters cubed. We can also write it as what? 1,000 cc. We can write it as 1 liter. We can write it as 1,000 milliliters. Right? There's many different ways to write it. 1,000 centimeters cubed, 1,000 cc, 1,000 milliliters, or 1 liter. All equivalent. Questions so far? Okay, so the next property that we'll talk about, density. Right, so we did briefly address density last hour. Density is a measure of the amount of mass within a given volume of substance. Sometimes we talk about how heavy something is, but we really mean how dense something is. Right? If I say, what's heavier, rock or feathers? What's heavier? Well, most people are going to say rock is heavier. What they really mean is rock is more dense, right? If I have a little tiny piece of rock and I fill this room with feathers, which one is going to be heavier? Have more mass. The feathers are going to have more mass. But the rock we consider heavier because in given volumes, in the same amount or the same volume of rock versus feather, the rock is much heavier. Your second formula, density equals mass divided by volume. Given amount of mass, a measure of the mass in a given amount of volume is density. So, a typical bowling ball has a volume of about 375 centimeters cubed and a mass of 8 kilograms, 8.0 kilograms. What is the density of the bowling ball? Well, there's your formula. Density equals mass divided by volume. And I think some of you, maybe many of you, maybe all of you, can figure this out, right? You plug in, but I'm going to kind of talk through it in the way that I think you should approach problems going forward that might not be quite as straightforward. And I'm going to ask myself, what am I trying to find? I'm trying to find density. Do I know a formula, or what do I know? I know a volume, and I know a mass. Now, do I know a formula that relates density and volume and mass? Yes, I do. And it's this one, density equals mass over volume. I'm going to write out the formula, and then I'm going to substitute. Right, so what am I going to substitute? Well, density, okay, density equals, what's the mass? 8.0 kilograms. And what's the volume? The volume is 375 centimeters cubed. Now what am I going to do? I'm going to do the math, right? So I'm going to plug into my non-graphing calculator 8.0 divided by 375, and it's going to tell me that the answer is 0. Does anyone have a calculator? Yes. What did you get? 0.0213 or something, right? We're going to round that for reasons that you don't understand just yet, but we're going to get there. 0.021. Am I done? Yep. Volume unit for volume can be liters, but it doesn't have to be, right? It could be milliliters. It could be gallons. Could be centimeters cubed. Could be quarts, pints, whatever. So as long as we have a unit for liter, we can, sometimes you may answer a question or you may run into an application that requires a particular unit. In that case, we'll learn how to convert between different units. We'll do that very soon. But in this case, it doesn't ask for any specific unit, so we can just use it. So that kind of brings us to the next question. Am I done? No, I'm not done. Because I have a number, I plugged it into my calculator, I got a number, I'm real excited. But I also need a unit. And what's the unit? Right. Kilograms divided by, or kilograms per centimeter cubed. And so this is going to be the correct answer with a number and a unit. Questions here? Yep.
But if you have the decimal, then they start talking about significant figures. Say like not near significant figures.
Right. So then, well, we'll learn, like I said, very shortly, rules for rounding, right, with the correct, what are called significant figures. But that's not quite yet. Other questions? So, what should we do? Right. So water at room temperature has a density of about 1 gram per milliliter, or 1 gram per centimeter cubed. Remember, centimeter cubed and milliliters are the same. Here are the densities of some other common substances. The only one you need to remember is water. Right? Water is about 1 gram per centimeter cubed. The rest of these you don't need to remember, but it's to give you an idea of substances kind of around us. Air, 0.001 gram per centimeter cubed. Much, much less dense than water. Makes sense, right? Cork, right? Cork is a type of wood, right? It gets used in to close bottles and so on. Sometimes shoes have cork soles, right? And that feels really good. Those shoes tend to be really light. 0.25 grams per centimeter cubed. Some metals, copper, gold, right? 8.9, 19.3 grams per centimeter cubed. Those densities are quite high. So when we compare the densities of different materials, water has a density of 1 gram per centimeter cubed. If the density of an object is less than water, it's going to float on the water. If the density is higher than the water, it's going to sink in the water. So, a substance less dense than water will float in water. And so here is a picture of a cork. Right, this picture is not the greatest picture, but here's the cork. It's floating on water because 0.25 is less than 1. Right, and here's a penny. Substance more dense than water will sink. Right, pennies, actually these days pennies don't have much copper. In the old days they did. And so we'll pretend it's a really old penny. 8.9 grams per centimeter cubed, greater than 1. And it sinks in the water.
Is that why, like, oil and vinegar is split?
Yes and no. Oil and vinegar split for reasons that you'll learn in Chem 2, if you go in and take Chem 2. Basically, the molecules or particles of water and the particles of oil don't mix. They don't cling to each other very well. But the reason why the oil is on top of the water and not the other way is because of the density. Right? The oil is less dense than water, so it floats. If the oil was more dense, the water would be on top, the oil would be on bottom. Yep. Question?
Does it relate to like surface tension? Because sometimes we see like a fly standing on water.
That is another great question that you'll learn about in Chem 2, right around when you learn about oil and water. Surface tension has to do with the molecules of water kind of sticking to each other, right? And so there's a little bit of force there. And so if the thing like the fly or whatever is the force exerted by the fly downward through gravity is less than the force that's holding the water molecules together, then it'll float. But once the surface tension is broken, it depends on density. Okay, before we get there, other questions here? Okay, so this is the question we just did. I'm doing this, I don't have an eraser. Okay, that's okay. I want to do something else here. Okay, so a certain metal has a density. A certain metal has a density of 4.0 grams per centimeter cubed. And I have a piece of that metal with a volume that's 2.5 centimeters cubed. Can I find the mass of that piece of metal? Yes, you can. Yeah, I'm asking you because you can. That's a great answer. I asked a question, you gave me an answer. That's not really the answer I was looking for. I should have asked a different question. How can I find the mass of that piece of metal? Okay, so there's two ways to do this, and they're mathematically equivalent, and we can, and it doesn't really matter which one we do. The formula is here, right? Density equals mass divided by volume. So I'm going to abbreviate density equals mass divided by volume. And so I'm given the density, 4.0 grams per centimeter cubed. And I'm given the volume. And I need to find the mass, right? So equals mass divided by 2.5 centimeters cubed. So, in principle, if I have a formula with three components, right? Density is one of them, mass is another one, and volume is another one. And I don't have the colored chalk either. That's okay. I know two of them. I know the density and the volume. That means I can solve for the third. How am I going to solve for the third? Well, I need to get m by itself, right? How can I get m by itself? Well, if I multiply 2.5 centimeters cubed, what's going to happen? Cancel, cancel. If I multiplied by 2.5 centimeters, and so that gives me m by itself. But whatever I do to the right, I have to do to the left. It's an equation, right? So on the left, I'm also going to multiply by 2.5 centimeters cubed. Right? So what I'm going to do when I do that is I'm going to get the following. 2.5 centimeters cubed times 4.0 grams divided by centimeters cubed equals m, right? Because the 2.5 and the 2 centimeters cubed and the 2.5 centimeters cubed canceled out, right? This is, there's a little trick here, right? And some of you may have noticed what I did, some of you maybe didn't. Just like if I have 2/3 times 3/4, and I multiply that, the 3 and the 3 cancel, that's the same thing I did here. 2.5 centimeters, except instead of just numbers, I also have a unit. And the units behave just like numbers when they're canceling out. So what's going to happen here? The 2.5 can't cancel with anything, but the centimeters cubed can cancel with the centimeters cubed. And when I do the multiplication, I get 2.5 times 4.0. That gives me 10. And what unit is left? Grams. 10 grams equals the mass. Questions here? The other way that I could have done it, and some students prefer to do it this way, is I could do density. I'll start with density equals mass over volume. And what do I need to find? I need to find mass, right? So I'm just, instead of manipulating numbers and units, I'm going to manipulate these variables, these letters. So if I want to get m by itself, what can I do? And try to cancel out the v. How can I cancel out the v? Multiply both sides by v. So v, v, and I get v times d equals m. And what's v? V is 2.5 centimeters cubed. What's d? 4.0 grams per centimeter cubed, and m is m. So I plug straight into that, and I do the same, and I get the same calculation. Some people like to do this, right, because it's okay. Then at this point, we'll take a 10-minute break, and we'll keep on going after that. So this is Chemistry 108, Chemical Principles 1, and we're continuing February 3rd, 2015, second half of the lecture. Okay, so we've talked about units, right, and numbers and units, and we've done so in a very kind of non-systematic way, right? We've introduced different units for different properties. Now we're going to take a more systematic look at units, particularly in the metric system. Now the metric system is a family or a system of units that is used in the scientific world. Not only in the scientific world, but particularly in the scientific world. So different properties of units, metric, or SI, this French for System International or International System. The base unit for mass is a unit called kilogram. We've talked about kilograms. The base unit for length is meters, abbreviated m, kilograms kg. Time, seconds, s. Temperature is going to be Kelvin, K. And the beauty of the metric system is that these base units can be modified with prefixes. So, for example, meters, meter is about this long or so. If you put a prefix called centi in front of it, you change the distance from a meter to about a centimeter. Or if you put a kilo in front of it, you change it from a meter to, I don't have arms that long, but a very large distance. So you can cover basically broad, wide ranges of size, mass, length, time, just by changing the unit. And the unit deals with powers of 10, right? And we know that powers of 10 tend to be easy to do calculations with, right? You multiply something by 10, what do? You add a 0. You know, multiply it by 100, you add 2 zeros, and so on. And so here are some examples of prefixes, right? There's 100 centimeters in a meter. There's 1,000 grams in a kilogram. There's 1,000 milliliters in a liter. There's 1,000,000 microliters in a liter, and so on. These are just a few examples. You don't really need to write them all down, because in the next slide, what we're going to get is a much more systematic view. right? So starting from really big to really small. Giga is 10 to the ninth. What is 10 to the ninth? 10 to the ninth, I made that face because I almost tripped on this wire here, is 10 times 10 times 10 times 10 times 9 times, right? That's what the exponent means. So 10 to the ninth is essentially 9 zeros. So that's really, really big. Where have you met this prefix giga before in everyday life? Sorry? Gigabyte. So on your phone or your computer. So gigabyte or gigahertz, maybe, if you're looking at the speed of your computer. And then as we go down, mega, 10 to the sixth. Kilo, 10 to the third, or 1,000. Centi, 10 to the minus 2. There's more prefixes. Here are some of the common ones. In other words, the ones you need to know. 10 to the minus 2. That means if I put the centi in front of something, I'm making it smaller. Smaller by how much? 100 times smaller. 0.01 is 1/100th. I'm going to interject something here. So if I make if I have 10 squared, that equals, just like I was using m meters cubed, it's 10 times 10 equals 100. Right. If I have 10 to the minus 2, if I have a negative exponent, the negative tells me I want to make it into a fraction. So it's going to be equal to, or an inverse, 1 divided by 10 squared. Divided by 10 times 10 equals 0.01. So that's where this comes from. The 10 to the minus 2 is 0.01. Another, incidentally, when we have a 0.01, it's valid, it's not incorrect to write 0.01, right, and leave off the 0. However, this is much, much preferred. Why is that? Because let's say I wanted to put in 0.32 liters of something. You know, if I wanted to give 0.32 liters of an IV bag to my patient, and I left off the 0. Okay. But I was writing real quick, and I just made a little dot like that. And I wrote, and I'm the doctor, I wrote my prescription, 0.32 liters. And the nurse saw that and said, 32 liters. You have a problem, a big, big problem. Right, so in this class, let's do that. Right, 0.32. 0.01. Milli, 10 to the minus third. Small m, big M. Okay, it's micro, 10 to the minus sixth. This is a Greek letter mu. You write it like this. It's kind of like a funny looking curly M, or you could also, sometimes some people write it that looks like kind of a U with a tail. It's the Greek letter mu, their equivalent of M. Nano, 10 to the minus ninth, something very, very, very small, right? And so at one point in the evolution of Apple, there was an iPod Nano, right? That was the little tiny one. Pico, femto. These generally only get used in scientific applications. right? In my other life, besides teaching, I have a research lab. We work in biological mass spectrometry. We use very, very tiny amounts of protein. We use picomoles and picograms and femtomoles. This table is in your textbook, and so you won't need to copy everything down, although you look in your textbook and you'll be able to find what these mean, what these are. You will eventually, by the time your first exam rolls around, need to know what these are and know how to use them, right? I'm going to show you how to use them soon. Yep. Questions? Okay, so I'm going to start how to use them. Right. So we could say something like this. How many meters are in 5 kilometers or kilometers? I think you could say it either way. And we're going to do it this way. Well, what do I know? I know I have 5 km. And what does this meaning actually mean? I just took out a little part of it so we could use some more space here. That means there are 1,000 meters, 10 to the third, or 1,000 meters in 1 kilometer. And so we're going to do a little exercise here. I'm going to find some space, and I'm going to take a little detour, and we're going to go back to fractions. Right, so if I take some number, and let's say 37, and I multiply it by 1, what do I get? 37. Right, if I take 222 and I multiply it by 1, what do I get? 222. Take anything multiplied by 1, what do I get? I get the same number, right? So if I take whatever, I multiply it by 1, I get the same number. 1 is 1, but 1 can also be also be written many different ways without changing the value of 1. For example, if I were to write, instead of 1, 1 over 1. 1 over 1 is 1. What if I were to write 10 over 10? 10 over 10 is still equal to 1. So if I multiply 37 by 10 over 10, I'm still going to get the same, right? 37. If I multiply it by 100 over 100, I'm still going to get point taken, right? So remember, when we're multiplying, as we saw somewhere around here, the units behave just like numbers. So let's say I had, instead of 100, I had 100 meters over 100 meters. That still equals 1. Right? The top and the bottom cancel. Let's just say now I left out the 100 and I just had meters over meters. That's still equal to 1. So finally, let's say I use this definition up here in green. 1,000 meters equals 1 kilometer. Well, if I said 1 kilometer over 1 kilometer, that would give me the same value. But wait, 1 kilometer is the same as 1,000 meters. So if I change this 1 kilometer to 1,000 meters, I have not changed the value of this fraction. That's just like saying, instead of 4 over 4, I get 2 plus 2 over 4. Right? This is still 4 over 4. This is 4. It just doesn't look like a 4. this is a kilometer, it just doesn't look like a kilometer. But when but they are in fact equal. And if I multiply this by this, whatever comes out on the other side is really the same as this. So if I take 5 kilometers and I multiply by, okay, so that's not a good example there. That's not the right way. That was an old presentation. If I take my 5 kilometers and I multiply that by 1 kilometer is equal to 1,000 meters, whatever that I get on the other end equals 5 kilometers. What I get on the other end, however, might look a little different. It's going to have the same value, but it'll look a little different. What am I going to do? I'm going to cancel my kilometers and kilometers because I have one on the top, one on the bottom. And I'm going to do my calculation. 5 times 1,000 equals 5,000. My kilometers and my kilometers canceled. What's left? What's left is just meters. So 5,000 meters. So how many meters are in or are equivalent to 5 kilometers? 5,000 meters. Let's do another problem. How many grams are present in 1,000 micrograms? How many grams are, that's a question mark here. How many grams are present in 1,000 micrograms? Well, I'm going to start again with what I know. Right? This is always a good principle. Start with what you know. I know I have 1,000 micrograms. So I'm going to write down my 1,000 micrograms. Remember the symbol for micro? It's this funny looking mu. And I'm going to, if I haven't remembered it yet, I'm going to look at my table and I'm going to say 1 microgram equals 10 to the negative 6th. 10 to the negative 6th grams. So I'm going to say 1 microgram and what's going to go here? 1 microgram. What's going to go on top? 10 to the negative 6th grams. And when I do this out, what I'm going to get is 0.001. And what's the unit here? Grams. Why is it grams? Because the micrograms and the micrograms canceled out. And what I'm left with is grams.
So you basically took away 6 zeros from...
That's one way to look at it, right? So one thing you could do is plug it into your calculator, your scientific non-graphing calculator, and you can get this. Or if you know how to use exponents and powers of 10, you'll notice that this is that 10 to the minus 6th is multiplying by this. Multiplying by this means you how can you do that as a shortcut is just to move the decimal place over 6 times. 1, 2, 3, 4, 5, 6. Another way to look at it is, what's 1,000 as an exponent of power of 10? 10 to the third, right? When you multiply powers of 10, or when you multiply exponents with the same base, what do you do to the exponents? Well, you add them, right, if you're multiplying. But you're going to subtract because it's negative. So it's 3 plus negative 6, or 3 minus 6 is 10 to the minus third. So it's very good to understand how to do it, right, without your calculator. If you have to use your calculator, well, you're allowed to. Here are examples of what we call dimensional analysis. And the point behind dimensional analysis is that units behave like numbers when they're multiplied or divided. Another terminology that's used to describe dimensional analysis is called the factor label method of solving problems, because you're using factor labels, right? You're canceling out the labels. So units behave like numbers when they are multiplied or divided. And so we went through this, right? If you do length times width times height, you get 1 meter times 1 meter times 1 meter equals 1 meter cubed. This is showing us that units behave just like numbers, right? We saw that already. Let's say we want to do a common kind of conversion. Right, there's 2.54 centimeters in 1 inch. That's something that's good common knowledge to have, because sometimes we have to deal with centimeters and inches. Right, so to convert from inches to centimeters, we're going to take the number of inches and multiply by 2.54 centimeters divided by 1 inch. Right, this is what's called the conversion factor. We did this without even really thinking about names and what to call stuff. But the 2.54 is a conversion factor. This 1,000 meters per over 1 kilometer is a conversion factor. It's called a conversion factor because it converts kilometers into meters. Right? This 10 to the negative 6 grams is equal to 1 microgram. That's a conversion factor because it converts micrograms into grams. And this converts inches into centimeters. So we do an example. How many centimeters are in 5 inches? 5 inches. We start with 5 inches. And then we're going to use this equality as a fraction. Now, how do we know this is whether the 2.54, whether it's 1,000 over 1 or 1 over 1,000? Well, we'll see. 5 inches times 2.54 centimeters per inch. What cancels out? The inches and the inches have to cancel out. Right? So the one you cancel goes in the bottom. The one you want in your answer goes on the top. So the inches times the inches cancels out, and you get centimeters left. You do the math, and you get 12.7 centimeters. This is what I'm talking about when I mention maybe you know how to do this, right? Maybe you know how to do this without setting it up the way I'd like you to set it up. I'd still like you to set it up the way I'd like you to set it up. I'd still like you to set it up this way, because as we move forward, the problems will get much more complicated, right? And if you get familiar using the method with simple calculations, the more complex ones will seem easier. Okay, so is the attendance